Okay, this is video 1 for the simple harmonic motion unit. Now, AP Physics is broken up into 7 big ideas. For this unit, we're going to be covering big idea 3 and 5. So the interactions of an object with other objects can be described by forces, and changes that occur as a result of interactions are constrained by conservation laws. The learning goals, the things I'll be grading you on. I can calculate the period of an oscillating system. I can explain the model for finding amplitude, and I can find the energy of an oscillating system. All right, so to get us started with simple harmonic motion, first off, we need to talk about, what is it? And basically, it's described by the motion of an object that's moving back and forth across some rest position. So in this picture, imagine that we have a spring, and let's say that this right here is the rest position, and this spring is going to oscillate back and forth across that rest position. So some knowledge for this: restoring forces can result in oscillatory motion. Looking at this diagram up here, the restoring force would be the elastic force. When a linear restoring force is exerted on an object displaced from an equilibrium position, the object will undergo a special type of motion called simple harmonic motion. Now, for a spring that exerts a linear restoring force, the period, which means the time of oscillation of a mass spring oscillator, increases with mass and decreases with the spring stiffness. So let's work up a model that finds the period of oscillation. So if I look at this diagram right here, we can see that we have an elastic force that's at first pulling it towards the wall, and then when it goes past, once the mass goes past the equilibrium position, it's now pushing it away from the wall. So we have a force that is trying to restore the system to its equilibrium. So we have simple harmonic motion. Also, remember that this force is a conservative force, so we also can use conservation of energy. Now, when we look at this, I can begin by taking a look at the net force acting on, let's say, the x-axis. And I can see that it's going to equal negative elastic force. And I'm basing it off of this one right here. So I'm saying that everything to the left is negative and everything to the right is positive. Okay, so there's only one force acting on the system, so it's not in equilibrium. So this must equal MA. So just rewriting it a little bit, I can say then that MA equals negative KX. And the reason why I'm saying just X instead of like a delta X is because my initial position is, I'm just defining that to be 0. So, and my delta X would be X minus 0. So I'm just going to go with X. All right, now, remembering back a little bit, we can apply just a little bit of calculus to this. Acceleration is the second derivative of the position vector. So I can have this right here, and solving for the acceleration, I get this expression right here. This is something called a second order differential equation, and you will not learn how to solve these in high school. But there is a solution to this. I can find out what X equals. The solution to this is X equals some maximum X. So our maximum X will be like right here. It's like the furthest point from equilibrium that you can get. So this times cosine times the angular frequency multiplied by time. So this is the solution to this second order differential equation. All right, so some things that we have in here. First off, remember that angular acceleration is 2 pi times frequency. Also, in this problem, the angular frequency will be spring constant over m underneath the square root. Let's see. Also remember that frequency equals 1 divided by the period. Okay, I'm going to combine these two real quick. So I get 2 pi f equals k over m. I'm going to then put in my 1 over period. So I get 2 pi 1 over period equals square root of k over m. And then I'm going to solve this for period. And this gives me a model that calculates the period for this pendulum. Or I'm sorry, not pendulum, mass spring system. So this measures how many seconds it takes to go from this point right here all the way over and then back to its starting point. Okay, now minima, maxima, zeros of positions, velocities, and accelerations. These are all features of harmonic motion. And as a student, you should be able to calculate force and acceleration for any given displacement for this object oscillating. And it may sound kind of difficult, but honestly, all you're doing is using this model right here and finding acceleration. And then once you have acceleration and position or displacement, you can go on and find everything else using kinematics. And we'll get some practice with that. All right, the second type of oscillator that you are responsible for will be a pendulum. Now, for a simple pendulum, the period will increase with the length of the pendulum and decrease with the magnitude of the gravitational field. All right, so let's take a look at this one. This one's a little more involved. We're going to have to do a little more work with it. So first off, I have tension, a tension force. I have a gravitational force that's vertically down. And this gravitational force can be broken up into an x and y component. And the angle of the pendulum will be the same as this angle right in here. Now, another thing I can do, I know this is a curved path, but if it's small enough, I can consider this a straight path for a position x, and the string has a length L. Now, to calculate this angle theta then, I could use the sine function. I could say that sine of my angle equals opposite over opposite over the hypotenuse. Where I can consider this as being my, well, it doesn't really matter. I mean, the hypotenuse is going to be L as well. So right here's my right angle. This is going to be L as well. But I can find that. But here's something really neat. It's called the small angle approximation. Okay, what the small angle approximation says is that theta equals x over L. Now, this is only true for radians. And it's only angles less than 15 degrees. So take 15 degrees, convert that into radians, and then anything less than that, this expression right here works. And I'll try to work up an Excel document to prove that to you. All right, I think we have everything we need, so we can go ahead and get started. So if I take again, I'm going to say that everything to the left is negative, everything to the right is positive. So if I take a look at the net force on an x-axis, which you can see I've kind of rotated, that's going to equal negative FGX. Okay, this is not in equilibrium, so mass times acceleration equals negative, okay, FG, that's going to be mg, and then to get the x component, I have to use a sine function. So mg sine theta. At this point, notice that masses cancel. So I'm left with acceleration equals negative g. Now, using the small angle approximation, instead of sine theta, I can just have theta. And again, that's only true for angles less than 15 degrees. All right, and then I can do some more substitutions. For acceleration, I have the second derivative of position equals negative g, and instead of theta, I can have x over L. So another way of writing this then would be just to get our arguments. There we go. And here we have our second order differential equation. Just like with the spring oscillator, the solution to this it's the same exact solution. X max again is the amplitude. It's how far back away from the equilibrium position you start. Then, just doing some other things here. Remember that angular frequency is 2 pi times f. In this case, angular frequency would also equal g divided by L. It's under square root. And frequency equals 1 divided by period. I'm going to do the same thing that I did last time. Set them equal to each other. Replace the frequency with 1 over period. And then solve for period. And that gives us our model, which predicts the period of a pendulum. Right, that concludes video 1 for this unit.